pretty important part of the class. They're intended to replace the in-person lectures. So I hope that you take the time to watch them. They do correspond with the online textbook, the book that we'll be using for this course. Please follow along with these videos as you work through the textbook. Our first topic for today is voltage and current. But before we actually get to that particular topic, I want to take a little bit of a sidetrack at first and explain a couple of other important concepts. So one very, very important concept as we get started out in this course is this idea of abstraction. So abstraction is the act of hiding details when they're not really important to you. So the name of the course is Introduction to Digital Logic. And on this screen here you can see various layers of abstraction, of which the digital logic part starts to come in right around here. You see digital circuits, logic, microarchitecture, and on up. So we are going to spend the vast majority of the course from digital circuits on up. That's sort of the home of this particular course. However, the first few sections are going to deal with these lower pieces of the puzzle. We're not going to spend a whole bunch of time on them, right? That's kind of the purpose of abstraction. These down here are the details that are not particularly important to us. So we're going to cover them relatively quickly so that we can stay at these higher levels of abstraction up here and not have to worry about the actual devices, the actual physics behind the devices that we're talking about in the course. So for this particular video, we're going to start down here at the very bottom with physics, right? So the stuff that we're going to talk about is directly related to electrons, right? But before we get to electrons, a couple other important topics to think about as we go through. A lot of what we're going to be talking about in this course are very complex systems, and these complex systems can be very difficult to work with and to just track mentally. And so in order to sort of manage these complex systems, we have a few tools at our disposal, a few principles that we like to apply when dealing with these complex systems that you can see on the screen here. So the first one is keeping things in hierarchies. You actually use hierarchies all the time. A classic example of a hierarchy is a state that is broken up into many counties, which might have many cities, which might have many neighborhoods with many streets, etc., etc. So that's an example of a hierarchy. A hierarchy is just taking a very large, complex system and breaking it into modules so that each module can then be examined individually if necessary. Which leads us to the second topic, modularity. So these modules, in order to be efficient, in order to be effective, should be very well-defined functions and should have very well-defined interfaces. So the inputs and outputs to these modules should be very, very well-defined. This is going to become particularly important when we start talking about VHDL sometime in the next week or two. The reason modularity is so important is because it limits the amount of side effects that can be introduced to a particular module. The final concept that's worth talking about right now is regularity. So not only do we want to break things into modules, and we want those modules to be efficient, effective, right? But we also want them to be uniform. We also want the modules to be, if I have two modules that are intended to represent the same thing, I want them to be the exact same thing. I don't want to have two slightly different modules. That's just going to add complexity and add confusion to the system. So really, regularity is trying to promote this idea of reusability. If I define my modules well, I can kind of plug them in whenever I need to. So that's a few important concepts to keep in mind as we go through the rest of the class here. Okay, let's move on to the topic at hand, which is voltage and current. So I like to use an analogy of pipes, water pipes, to kind of define the main concepts of electrical systems. So if we think about a series of pipes, plumbing, right? That might be in your house or in your apartment. Voltage then can be thought of like a pump. Voltage is going to take water that's moving relatively slowly or perhaps not at all and make it move faster. It's going to add energy to that water and make it move faster. That's the role of voltage in this system. So voltage, of course, is measured in volts. The second component of electrical systems is current. So to visualize current, in using our water analogy, you would think, how fast is the water moving through the system, through the plumbing? That would be analogous to current in an electrical system. So in an electrical system, it's not water, it's electrons moving through wires. So once voltage is applied to a system, those electrons start moving with a certain speed. Speed is not really quite the right word to use, but good enough for our purposes. And so how fast those electrons are moving through the system is represented by current, which are in units of amps. And then finally, resistance. Resistance is kind of a counterbalance to current. It slows things down, in other words. So resistance, in using our water analogy, would be the pipe getting smaller at a particular point. So there'd be a bottleneck in the pipe, in the plumbing. Once the water gets to that point, it has to slow down a little bit. It can't all fit through as much, right? The water can't fit through the smaller opening in the pipe, so it has to slow down in order to make it through. So those are the three primary components of electrical systems. There are some more that we'll talk about perhaps later on, but those are the three that we need to know right now. And these three particular components lead to a very famous law that you may have seen before called Ohm's Law, that states that the voltage of a system is equal to the current in the system times the resistance in the system. So this law is useful not just in this form, but in its other forms as well. Basically, if I know any two of these three, I can find out the other one, right? So if I know the voltage and the resistance, I can determine the current, or if I know the voltage and the current, I can determine the amount of resistance in the system. Just to give you a little example of how Ohm's Law is typically applied, here's a very simple circuit. So this is the first circuit we've seen in this class. On the left side, you'll see a schematic symbol for a voltage source. So here we see this voltage source is labeled with a value of 5 volts, right? And then on the right side, we see the schematic symbol for a resistor. Oh, I forgot to mention resistors are measured in ohms, which you see is represented with this omega symbol here, right? So on the right-hand side, we have a resistor that's 100 ohms. So if we go back to Ohm's Law here, we know the voltage and we know the resistance. What we don't know is the current, but we know enough to compute it. So the current in this case is going to be the voltage over the resistance. So with these particular numbers, 5 volts over 100 ohms will give us 0.05 amps of current flowing through the system. If I want to have more current flowing through the system, I can lower this resistance. So if I make the resistance lower, let's say I only have a 2 ohm resistor instead, that would give us 2.5 amps, right? Which is a much larger current than our previous example. And if I want to decrease the current, then I can, of course, increase the resistance as well. Or decrease the voltage, too. That would also be effective. So everything that we've talked about in the last few slides is actually in the realm of analog circuits. The name of the course is Digital Logic, which is not the same thing as analog. We'll get more into the distinction of those two in a little bit. But in order to understand digital logic, it's nice to have a good background in analog. So this is a quick and easy introduction to voltage, current, resistance, and analog circuits. In the next video, we'll start making a progression towards digital circuits and working our way up through the various levels of abstraction.